this is part 2 of the solution chapter, and in part 2 we're going to talk about the equations that describe solutions. And there's 3 equations we're going to use, and what I really recommend that you do is on an index card or a piece of paper, write down the 3 equations and then have them in front of you at all times. So label them as what type of problem will use this equation and write the equation, and that'll help you to know. And as you approach each problem, think, which equation do I use? And then that'll help you apply it to solving the problem. So the first equation is mass percent. So mass percent is like percent always has been, that it's the part over the whole times 100. And so percent has always been that, and that's what it is for this equation here. And so the part is the grams of solute, the whole is the total, the grams of solute plus the solvent. So it wouldn't be just the water, it'd be the water plus the salt or whatever else is added in it. And then times 100, and that's your mass percent. So let's try this practice problem here. So a solution is made from 12.6 grams of NaCl and 100 grams of water. So you can see this is our solute and this is our solvent. So our numerator is going to be the 12.6 grams. The denominator is going to be 100 plus 12.6 grams times 100, and that's going to be our percent. Okay, so it's the part over the whole times 100. So let's go to the next slide, and it has it written out a little more clearly, and you can see that work. So there you see that it's the part over the whole times 100, and that's mass percent. So that's one way we can use the mass percent equation. Now another way we can use the mass percent is in a calculation. So sometimes we know the mass percent and we're trying to find either the grams of the solute, the solvent, or the grams of the solution. So here's a problem here. A solution contains 20.1% HCl. What mass of the solution is needed to provide 30 grams of HCl? Okay, so let's think of it in terms of given and find. Okay, so what we know is 20.1% HCl. Okay, that's our given. And then what mass of solution? So that's our find. Grams of solution is needed to provide 30 grams of HCl. So that's another given. 30.0 grams of HCl. Okay, so in this problem we have 2 numbers in our given column, and so one of them is going to be our starting number and one's going to be a conversion factor. And it turns out that this percent is actually a conversion factor. So we can write a percent as 20.1 grams of HCl per 100 grams of solution, because that's what percent means. All right, so we change our percent into a conversion factor, and then we can use our grams of HCl as the starting number, 30.0 grams of HCl, and then we use our conversion factor. Now we see the HCl on the top, so we want HCl on the bottom. So we put 20.1 grams of HCl down here and 100 grams of solution on the top. And then you can see the grams of HCl cancel, and that's going to give you the mass of solution. So you take 30 times 100 divided by 20.1. Okay, and so the next slide is going to show that a little more clearly. So there you see the conversion factor, and then that gives us the grams of solution. Okay, so this is the unit analysis method. There's really 3 methods that we can use, just like our density problems. 3 methods. I'm only going to teach you the unit analysis because I think it's the most important method. It's the most applicable to all kinds of problems. So if you want to look at the other methods, they're on the next slide. If this one makes sense, you can skip the next slide. So the next equation is molarity. So remember I said there's going to be 3 equations. This is number 2. So number 1 was the mass percent. Number 2 is molar concentration. So molar concentration, there's 3 things that you'll see. You'll see molar concentration, you'll see molarity, and you'll see capital M. So those are the 3, and they all mean the same thing. So whichever one you see, it's the same thing. And so notice the equation is moles of solute per liter of solution. So moles on the top, liters on the bottom. It's not liters of solvent, it's liters of solution, and usually that will be given in the problem. And now some problems will start out giving you grams, and you've got to change grams to moles, but that's something we've done a lot of, so that shouldn't be too hard to do. So just remember that you need to do it. So let's apply this to a problem. So what is the molar concentration of a solution made by dissolving 15.0 grams of KNO3? So that's going to be our moles, and in 150.0 milliliters, that's going to be our liters, okay? So that's the equation, but notice that we don't have moles and we don't have liters, so we have a little bit of converting to do. So let's start with our 15.0 grams of KNO3. Now the first thing we have to do is change that to moles, okay? So we have to add up the molar mass of KNO3. So we find the mass of the K, the N, and 3 times the O. And that turns out to be, well, let's add that up. So I'm going to start with the O. That's 16 times 3. And then plus the nitrogen, 14.01. And then plus K is 39.1. And I get that it's 101.11. So 101.11 grams per mole. So that gives us the moles of KNO3. And so we want the moles divided by the liters. Now we don't have the liters, we have the milliliters. So I'm going to just move the decimal, 1, 2, 3. So I'm going to call it 0.1500 liters. Okay? And so now our grams cancel, and we have moles per liter. So I go to my calculator, 15.0 divided by 0.15 divided by 101.11 equals, and I get that that's 0.989 capital M moles per liter, or you can write out moles per liter. So showing that on the next slide a little more clearly. There we go. All right. And so that's how you find moles per liter. Now again, we can use molarity in a calculation. Sometimes we're given the molarity and we need to find either the moles or the liters or possibly the grams. And so the next problem is a problem like that. And again, there's 3 methods. I'm going to show you unit analysis because I think that's the most useful. So here's our problem. How many milliliters of 0.115 molar sodium hydroxide solution are needed to provide 2.90 grams of NaOH? So we're given 0.115 molar NaOH, and we're also given 2.90 grams of NaOH. And what we want to find, the defined is often the very first thing. It says how many milliliters. So we're looking for milliliters of solution. All right. And again, we have two things in our given column. One of them is a conversion factor. And the one that's the conversion factor is capital M. So I don't like to use capital M. I cross it out and go with moles per liter. So now you can see that's a conversion factor. Okay. So the 2.9 is our starting number. So we start with the 2.90 grams of NaOH. Okay, now we can't use the grams because we need moles. So the first thing I'm going to do is change grams to moles. So I need a molar mass of sodium hydroxide. So again, I go to my periodic table. Sodium 22.99 plus O 16 plus H 1.01, and that gives me 40. So that's going on the bottom. 40.0 grams per mole. So now I have this sodium hydroxide in moles. Now I can apply my conversion factor, and I want the moles on the bottom. So 0.115 moles of NaOH per, on the top, I have 1 liter of solution. Okay, and now actually it asked us for milliliters, so I'm going to say 1 liter is 1,000 milliliters. Okay, and that'll give me my answer. So going to my calculator, I do 2.9 divided by 40 divided by 0.115 times 1,000 equals, and keeping 3 significant figures, I'm going to go with 630, and I'm going to put the decimal in to show that the 0 is significant, milliliters of solution. Okay, so that's the unit analysis method using the molarity as a conversion factor. So again, I'm a little more cleanly on the next slide. And so my hint, it's kind of covered up in the letters. Don't use capital M. Change it to moles per liter so you can see it's a conversion factor. So here's the calculation a little more clean. Okay, so that's using molarity as a conversion factor. And again, if you want to use the triangle or algebra, those also work. But if this makes sense, it's the best method, and you can skip the next slide. Slide shows you the other methods. And here they are if you want to look at those. Okay, so now we're on equation number 3, and that is for dilution. So the dilution equation is right here. M1V1 equals M2V2, okay? Sometimes as a solution is made, rather than putting a solid in water, you make a solution by taking a more concentrated solution and diluting it. And this happens if you've made like orange juice from concentrate or something like that. That's the idea of a dilution. So M1V1, the original molarity, the original volume, is equal to M2V2, the diluted molarity, times the diluted volume. Okay? Let's see how this one works. In a dilution procedure, preparing a less concentrated solution from a more concentrated solution, the thing that remains the same is the moles of solute. So all you're doing is adding water, you're not adding more solute. And so that's how it works. And so here's a problem for us to do. So what volume of 6 molar NaOH needs to be diluted to prepare 5.00 liters of 0.1 molar NaOH? Okay, and so let's identify, so our equation is going to be M1V1 equals M2V2. And when we look up here, let's identify this. 6 molar NaOH, well, that is our M1. Do we know our V1? No, that's our question. So our V1 is our find. Okay, so that's M1 and V1. And then we come down here. this is our V2 right here, and this is our M2 right there, okay? So we just put in what we know. We're going to solve this algebraically because that's the easiest. So M1 we know, it's 6.0 molar. V1 we don't know, that's the variable we're solving for, equals M2, that's the 0.10 molar. That's V2, M2, and our V2 is 5.00 liters. Okay, and we just solve it algebraically. Notice we want to get V1 by itself, so we're going to divide by 6.0 molar, divide this by 6.0 molar. So notice this cancels, the molars cancel, the M cancels here, okay? And now we just go to the calculator. We do 0.1 times 5 divided by 6 equals, and I get 0.08, and let's keep just two significant figures. Remember, the first two zeros are not significant, so we keep the 8 and then the 3. And the units on it are liters, because that's what we have left right here is our liters. Okay? So that's how we apply that equation. You know you're using the dilution. It'll usually say dilute in the problem. And so here you see it a little more cleanly. And our last type of equation, and it's not a new equation, we're using still the molarity equation. So that's the same one that we've used before, but we're going to apply it a little bit differently in a stoichiometry. So we're going to apply it to a reaction. So it's still the molarity, but we've rearranged it so that we have moles equals the liters times capital M. Remember our capital M? What does that mean? That is moles per liter. Okay, capital M always means that, and so you can see how that turns out to be moles. And so since it can find moles, we can apply it in situations where we're trying to calculate quantities from a chemical reaction. So if the volume and molarity of a solution are known, you can use this to find the moles. Then those moles can be used in a mole ratio for a reaction. Okay, so that's stoichiometry. So let's see how this works. So let's apply this to a problem here. So here's a solution stoichiometry problem. The question is, what mass of silver bromide is produced from the reaction of 37.5 milliliters of 0.1 molar aluminum bromide with excess silver nitrate solution? So there's kind of two ways to set this up. The given and the find. Let's go ahead and do that first, okay? So the given is right here. It's the 37.5 milliliters, 0.1 molar of aluminum bromide. So you see that here, 37. And remember, don't write capital M, write moles per liter, and that's going to be more helpful. Okay, so we'll change the capital M to moles per liter. Now the excess silver nitrate, all that's telling you is you don't have to worry about the silver nitrate. You have plenty of it, okay? So another way to think of it is write it underneath. So we're talking about the aluminum bromide. So we have 37.5 milliliters, and we know it's 0.100 moles per liter. Okay, so we know that. We don't have to worry about this one because we have excess. And what we're trying to find, so our find is the silver bromide. That's this one. So we're looking for grams of silver bromide. Okay, so that's kind of how we set up the problem. And so our given, again, we have two things. We have the milliliters and the molarity. The one we're going to start with is the milliliters. So we're going to start with 37.5 milliliters of AlBr3. Okay, and the molarity is our conversion factor. So since it's moles per liter, we want the liters on the bottom. However, we have milliliters here and liters here. So what I'm going to do is I'm going to say this is 1,000 milliliters, because 1 liter or 1,000 milliliters, they're the same thing. Okay, so 1,000 milliliters has 0.100 moles of AlBr3. Okay, so let's go ahead and put that AlBr3, AlBr3. It helps us keep track of what compound we're talking about. So now the milliliters cancel. We're at moles, and so from moles, it's time for the mole ratio. So here's where we go to the balanced reaction. So moles AlBr3 are here, so we're going to put those in the bottom, moles AlBr3, and the number is right here. It's 1. So 1 mole of AlBr3. So that's our given. That's what's going to cancel. And what we're trying to find is the AgBr, and that has a 3. So 3 moles AgBr. So this is that very important mole ratio step where we change from moles of our given to moles of our find. Okay? And then the last step, we're looking for grams. So we have moles, we're looking for grams, so we need to add up the molar mass. So here I go to my calculator. Ag is 107.87 plus Br is 79.9, and that gives me 187.77 grams of AgBr per 1 mole of AgBr. Okay, and so the moles AgBr cancel, and we have grams of AgBr, which is what we're trying to find. So I go to my calculator. The 187 is in it, so times 3 times 0.1 divided by 1,000 times 37.5 equals, and I get 2.11 grams of AgBr. Right? So that's how you do the stoichiometry problem. And the last things aren't really equations, but there are other solution principles that are important. The first one is how a solution affects the freezing point or the boiling point. So if you have pure water, it will freeze at 0 degrees Celsius and it will boil at 100 degrees Celsius. But then if you add a solute to it, like salt or any solute, what happens is it lowers the freezing point and it raises the boiling point, okay? And the book goes through how to calculate these. We don't need to calculate them. Just realize that this is a principle that happens. And some examples is making ice cream. If you've ever made ice cream, you add salt to the water, to the ice, and it helps it freeze at a lower temperature. And the antifreeze in your car, you put that, a mixture of antifreeze and water, and what that does is it makes the water freeze at a lower temperature so your car doesn't freeze in the winter. And the next one is osmosis. So osmotic cells have something called a semi-permeable membrane. And it's a membrane through which the water can flow, but ions and other particles cannot flow. And this is really important in cells because cell membranes are semi-permeable, and water can flow in and out, but the contents of the cell don't. And so what happens is the water flows towards the more concentrated solution, trying to make them equal. So here you see there's ions or particles, so the water is going to flow this way, trying to balance them out. And that's how osmosis works. So an example of osmosis is in blood cells. So isotonic means that the concentration on the outside and the inside of the cells is the same. And that's important. That's the right kind of solution to have. If it's hypertonic, so here the solute concentration is higher on the outside. So this is like putting the cells in salt water. And what happens is the water will flow out of the cells and into the water and make them shrink. Or if it's in hypotonic, where the solution is lower concentration that they're in, and so that's like putting pure water, blood cells in pure water, the water will flow into the cells and can swell and even rupture them. So what do you need to know from this chapter? You need to predict what substances will dissolve in water and in a nonpolar solvent. Identify general trends in solubility with increased temperature and pressure. So that's whether it's a solid dissolved or a gas dissolved, and they're a little bit different. And then here's your calculations that we've just talked about: the mass percent, the molarity, and the dilution, and then also apply molarity to stoichiometry problems.